Next, we'll carry what we learned about finding the hydronium ion concentration of a weak acid solution one step further and determine the pH of that solution. Here we're asked to find the pH of a 0.2 molar nitrous acid solution. The reaction is nitrous acid plus water yields H3O++ plus the nitrite ion. So we prepare our ice table as before. Initially, we have 0.2 molar of the nitrous acid and essentially no hydronium ion and no nitrite ion. We're losing X of the nitrous acid, gaining X of the hydronium, and gaining X of the nitrite. So at equilibrium, we'll have 0.2 molar minus X of the nitrous acid, X of the hydronium, and X of the nitrite. So we set up our Ka here. That's products over reactants. Now remember, we don't count the water as a reactant because it's a liquid and its concentration isn't changing. So that gives us hydronium ion and nitrite ion as products and the nitrous acid as a reactant. So we have hydronium times NO2 minus the nitrite over nitrous acid equal to the Ka for that acid. So that gives us, since the hydronium is X and the nitrite is also X at equilibrium, and the nitrous acid is 0.2 minus X, that gives us X squared over 0.2 minus X equal to the Ka for the acid, which we can look up in a table. So we can assume that X is small because the Ka for this acid is 10 to minus 4. Well, that might not really be true because 10 to minus 4 is a pretty big Ka. So we're just going to go ahead and make that assumption here and then check to see if the X is small approximation is valid. Okay, so if we assume X is small, that gives us X squared over 0.200 is equal to the Ka. We can take the square root of both sides and we end up with X equal to 9.6 times 10 to minus 3. Now if we check our X is small approximation, that's the thing that we subtracted over the thing we subtracted it from times 100, we get 4.8%. So that's almost 5%. It might be good to go back and plug in and work this with the quadratic formula, but we'll go ahead and move forward since this is barely valid. Now we're going to find the pH of the solution. So our hydronium ion concentration was equal to X, and that is 9.6 times 10 to minus 3. So the pH is the negative log of the hydronium ion concentration, just as we saw with strong acids, except that we had to solve for the hydronium ion concentration here. So the pH is negative log of 9.6 times 10 to minus 3, which gives us a pH of 2.02. Now we can check to see if that was valid by plugging the concentrations into our Ka expression. So we had the 9.6 times 10 to minus 3 times 9.6 times 10 to minus 3, so that gives us 9.6 times 10 to minus 3 squared over 0.2 for the nitrous acid concentration, and it gives us 4.6 times 10 to the minus 4, which was the Ka, so we can assume this was a valid approximation.